Welcome to this session on prioritizing technical debt as if time and money matters. So this is a broad topic, so I would like to jump right in and get started by looking at what forces do we have to balance when building large-scale software systems.
And these forces and challenges are well captured in something known as Lehman's laws. There are multiple laws of software evolution, and today I just want to present two of them to you here and see if they resonate with your experience. So the first law is the law of continuing change. This is where Lehman claims that the system has to continuously adapt and evolve, or it will become progressively less useful over time. Is this something you recognize? Yeah, I thought so. This is the very reason why we keep adding new stuff, why we keep adding new features to our existing products, because we need to keep them relevant. We need to respond to users. We might even have to respond to competitors. So successful software is never done. However, what I want you to do now is to notice that there is some kind of tension, some kind of conflict with the second law of software evolution. And that's the law of increasing complexity. And the law of increasing complexity claims that when a system evolves, its complexity will increase unless we actively try to reduce it. So do you see the tension between these two laws? On one hand, we have to continuously adapt and evolve our code. We have to add new features to it. But when we do that, its complexity will increase, which in turn makes it harder and harder to respond to change. And this is a vicious circle that we need to stay on top of and control. Otherwise, we end up with technical debt and excess complexity. And the main problem when that happens is that we tend to be aware of the symptoms, but not so much the real issues. And to make matters worse, we will notice different symptoms depending on who we are, what our role is. So let's, for example, say that we are in a technical leadership role. What will happen is that we will notice effects on the product roadmap. We might experience things like the lead times to implement a new feature. They get longer and longer and longer. And as a consequence of that, we will miss delivery dates, and most likely we're getting a really hard time to guess how long a particular feature will take. We lose predictability. So that's what the business sees. What our end users tend to experience is this. They tend to experience bugs, which are an effect on the external quality of the code. And the real root cause tends to remain largely hidden, opaque, and obscured. So to me, the number one challenge here is to bring visibility to technical debt. How can we do that? Well, over the years, I've seen a number of different attempts at this. One of them is simply to try to quantify technical debt. And the way this works is always that you have some kind of tool, and those tools, they have a number of hard-coded rules that they check for. So for example, the tool might scan a code base, right? And then it comes across a method that's overly complicated, lots of if statements. So the tool simply estimates that, hey, given this excess complexity here, this will take you 2 days to refactor. So now you have 2 days of technical debt. And then it continues to scan, and maybe it finds a public method without a comment, right? Something like that. And now the tool says that this is going to take 5 minutes to add a comment. So it sums it up and says that now we have 2 weeks and 5 minutes of technical debt, and it continues like that. So how well does that work in practice?
So as part of my day job, I analyze code. In practice, that means I go to different sites, I analyze their code bases, and I try to come up with recommendations and suggest improvements. And a couple of years ago, I worked with this really interesting organization that prior to my arrival had tried to quantify their technical debt. So what they've done is that they've taken a static analysis tool capable of quantifying technical debt and thrown that at their 15-year-old code base. Now, this tool reported that on your 15-year-old code base, you have accumulated 4,000 years of technical debt. 4,000 years of technical debt. Let's put that into perspective. 4,000 years ago, that was here.
That's the start of recorded history through the invention of writing. So, I'm always curious, what kind of programming language did they use for that code base? Most likely a Lisp, right? Or maybe Fortran. No, on a more serious note, I want to question this because 4,000 years of technical debt, it might very well be accurate because a lot of that code was written in parallel by having hundreds of people work on that code base. So it might be an accurate number. But how useful is it? How do you act upon information like that? What do you do? Is all debt equally important? And this is where it starts to become dangerous to quantify technical debt. Because what's very likely to happen next is that the organization is going to put a quantitative goal on the technical debt. And the way this works is typically that you say, all right, so we did this scan of our code and we found out that we have 7,000 major issues. We need to bring that down to 5,000. So let's invest 3 months into bringing them down. Now, when I hear that, I always advise against it. And the reason I advise against it is because we need to consider what kind of behavior that we reinforce by putting a quantitative goal on technical debt. Because what's going to happen is that we as developers, we're going to make sure that we meet the goal that we're being measured on. So we're going to do our best to bring those issues down from 7,000 to 5,000, most likely by picking the task that we might be the most familiar with, or the task that looks the easiest. And the reason this is dangerous, and actually I like to compare it to something like jumping from the 5th instead of the 7th floor, right? Most likely none of them are a good idea. And the reason I say this is because the most important aspect is missing. The most important aspect is the business impact. What I want to point out so far is that quantifying technical debt might be an interesting exercise. It's almost always depressing, but it's not actionable. More specifically, and this is really important, technical debt just cannot be prioritized from code alone. You know, what you see in the code might be possibly the cost for remediation, but it's not the cost of technical debt. At the same time, it's an important topic because we're always going to have this trade-off between improving existing code versus adding new features. Remember Lehman's laws, we need to keep them balanced, right? So we need to prioritize, but how? Well, for those of you who might have read one of my books or maybe even visited one of my previous talks, you know that I'm a big fan of version control data. Yeah, I guess we all have our odd hobbies. This one happens to be mine. And the reason I like version control data is because it's a virtual goldmine of information. In version control, not only do we know exactly which part of the system that were modified and when they were modified, we also know who did that change. And we can tap into version control and find patterns into how we, as an organization, interact with the code that we're building. And we can use that to prioritize technical debt. So let me show you how this is done on a real-world code base. And the code base that I'm going to demonstrate on is a code base that I think some of you might actually carry around in your pocket right now. I'm talking about this. I'm talking about Android. More specifically, I'm talking about the part of Android known as the Platform Framework Base. The Platform Framework Base is a pretty large code base, roughly 3 million lines of code, most of it written in Java, and tons of developers that have contributed. So what you see on screen here is something I call a hotspot visualization. Let me walk you through this visualization so that you know what you see. First of all, if you look at these large blue circles, the ones that blink on screen right now, each one of those represents a top-level folder. So if this was a code base that you worked on, your own code, they would recognize the names of those top-level folders as important subsystems or high-level modules, something like that. A hotspot visualization is also interactive, so that we can click on one of those circles and we can zoom in and navigate to the part of the code that we're interested in. And once we get to a lowest level, like here, you see that each file with source code is visualized as a circle. And you see that those circles have different size. Let's have a look at that. This is because size is representing the number of lines of code. So this is like a very rough complexity dimension, right? The more lines of code, the harder it is in general to understand that code. However, no matter what complexity metric we use here, it's still the case that just because some code is complicated, that doesn't mean it's a problem. Because code complexity has this property that it's only a problem when we need to deal with it. So even if we have some overly complicated code, maybe that code has been stable for 3 years, we never need to touch it, right? It might not be ideal, but we probably have much more urgent matters to attend to. So how can we find out about them? Well, this is where I turn to version control data. So I calculate the change frequency of each piece of code. I simply look at how many commits do we do to each file, and I use color to visualize that. And by combining these two dimensions, we can identify complicated code that we have to work with often. And that's our hotspots in code. From a technical debt perspective, I like to view the code complexity as the principal, right? That's the actual debt that we have taken on, whereas the change frequency is the interest rate on any technical debt we might have in a hotspot. Now, I'm going to show you how to dig much, much deeper, but before I do that, I like to point out that I simply don't like the word code quality. And the reason I don't like the word and the term code quality is because it kind of suggests an absolute, whereas the reality is much, much more complex. And this is something that's well captured in the following research paper, which is one of my favorites. It's a pretty old paper, but it's still very true today. And that paper claims that this idea that we can use a single number, no matter what it is, I'm going to give you some example on complexity metrics soon, but no matter what we choose, we simply cannot capture a multifaceted concept like code complexity with a single number. Instead, what I've done is that I've taken a lot of inspiration from the second statement here. Identify specific attributes of code complexity and measure these separately. So let me show you how that looks. I've been calling this concept code health. Basically, how healthy is your code? And this ties into maintainability and readability and understandability, all that stuff. Because the higher the code health, the better the chances that the developer can dive into that code, understand it, and comfortably change it. So what I do here is that I measure a bunch of aspects that are known from research to correlate with an increased risk for defects and increased maintenance costs. The code simply becomes so much harder to reason about. And just to give you some example what I look for, you have a small list here, but I typically start by looking for the big stuff, like is this module low on cohesion? That is, does it have too many responsibilities? Which is often the case with large hotspots. I also look for specific complexity patterns. One of them is deeply nested logic. So this is simply the case where you have if statements inside other if statements, and then a for loop or something for good measure. Complexity of that kind has a very strong correlation to defects. In fact, there's some pretty good research that shows that patterns like deeply nested complexity are responsible for roughly 20% of all programming mistakes. Then there's another pattern that I've written about on my blog that I call the bumpy road code smell. And this is simply when you have a function and there are multiple chunks of deeply nested logic inside that function. So deeply nested logic is a problem in itself, but when you have multiple chunks of nested logic inside the same function, it tends to be a very clear sign that that function is lacking on cohesion as well. So things like that, and you might see a few other examples as we go along. So by identifying these code health issues, I can make a quick assessment of the quality of that code, and I can basically figure out, is this something we need to refactor, or is it something we can live with? When I find a lower code health, what I do next is that I want to figure out, is this a problem that the organization is aware of so that we have already started to refactor that code? Or is it a growing problem? This is information that we can get from version control too. So what I do when I find a big hotspot, like the one you see here on screen, it's the #1 hotspot in Activity Manager Service. It's the #1 hotspot in Android. So what I do is I go to version control and I pull out each historic revision of that code. And then I count the number of lines of code over time. That's the blue line that you see. And I count the nesting depth, which is what you see with the red line. And what you see here is that the blue line the lines of code seems to grow over time. So there's an accumulation, and we might indeed have a problem with pure size here. But the red line, the complexity, grows at an even steeper rate. And what this indicates to me is that if we see this pattern on a hotspot with low code health, then it's very, very likely that we will have an even bigger issue in the future unless we act upon this, because this definitely seems to be a growing problem. And the reason I'm such a big fan of complexity trends and version control data is because they provide trends. And trends is something that I find actionable. A trend is much more actionable than any absolute values that you can mine out of the code. Because you can view it this way. I've probably talked to at least 200 different organizations over the past 5 years and helped them out with prioritizing technical debt. And until the present day, I have never ever met a single manager that told me that we want our code to be worse, right? So no matter what baseline you start from, you never want your code to get worse. And complexity trends help you visualize that. All right, so let's return to Android here. The number one hotspot, like I mentioned, is Activity Manager Service. The Activity Manager Service is a gigantic file, right? 20,000 lines of code. And to make it even more challenging, that code has been developed by 74 developers over the past 3 months. So even if we have all these indicators of a growing complexity trend and low code health, can we really act upon this? Who would like to have this refactoring task? Well, what I do when I find a hotspot like this is that I use a technique that I call X-ray. So I simply take that large file, I parse it into separate functions, and then I look at the git log, where do each commit hit over time, and I sum it up, and I get hotspots on a function level. And this is the data I use to prioritize a starting point for refactorings. Let's see how it looks on Activity Manager Service. We see that the number one hotspot in Activity Manager Service is a method called handleMessage. And we see from the change frequency in the table there that this method has been worked on 98 times just over the past year. So 98 commits just to that function. So that's like 2 code changes each week, right? So this definitely has an impact. And if we look at the last column, the one that says cyclomatic complexity. So cyclomatic complexity is another one of those complexity measures. Cyclomatic complexity is basically a count of the number of possible branches for a function, right? So you count the number of if statements, the number of loops and stuff like that. And cyclomatic complexity, the thing I like about it, it's a pretty rough metric, but what I like about it is that it's a pretty good predictor on the number of unit tests I will need to cover handleMessage. So for handleMessage, I would need at least 106 unit tests just to make sure I have covered it with tests. So that tells something about the excess complexity here. We also see from the column in the middle that handleMessage has 500 lines of code. That's a lot for a single function, isn't it? It is, for sure. But 500 lines of code is much, much less than 20,000 lines of code, which was size of the total hotspot. And it's definitely less than 3 million lines of code, which was size of the total Android code base. So more importantly, we are now at the level where we can start to act upon this information and do a focused refactoring based on data from how we, as an organization, have actually worked with the code. All right, now that we know what hotspots do, I would like to explain to you why hotspots work so well to prioritize technical debt. So please, have a look at the following graphs. They all show exactly the same kind of data. On the x-axis, you have each file in a system, and those files are sorted according to the change frequencies. That is, how many commits, how many changes have you done to that particular file? And the number of commits, the number of changes, is what you see on the y-axis. Now, if you look at those graphs, you see that I have examples from 3 completely different projects. Different projects with different lifetime spans, different programming languages, different scopes, different organizations, different developers. Everything is different. And yet, they all show exactly the same pattern. They show a power law distribution. And this is something I've found in every single code base that I've ever analyzed. And I probably analyzed around 300 code bases by now. So this seems to be the way software evolves. And this is important to us because this helps us to prioritize so that we don't have to fix all technical debt. Because what this data tells us is basically that most of our code is here, in the long tail, which means it's code that's rarely, if ever, touched. So this is the part of the code where we can actually live with some technical debt and be fairly confident that it doesn't have a huge impact. It can still be a risk, but it doesn't have a short-term impact. Most of our development activity, on the other hand, is going to be at the head of the curve, in a very small part of the code base. And that's the part of the code where, due to the high development activity, even minor code health issues can have a huge impact. The cost will simply multiply due to the interest, right? So what hotspots do is that they help us identify the head of the curve so that we can look for an overlap with code health issues and start to address the potential problems and be fairly confident that we will get a real return on the time we invest in refactoring code error. But there's more to hotspots. So in my latest book, Software Design X-Rays, I have this chapter that I called Your Best Bug Fix This Time. And what I did in this chapter was basically that I referenced some research that have studied how aging of software code impacts correctness. And what that research found was pretty fascinating. It identified that a module that is a year older than a similar module has roughly 1/3 fewer defects. So this is really, really interesting. So the older and more stable a code is, the less likely we will find any defects in it. And what hotspots do here is that they help us separate those stable parts of the code that are likely to be fairly correct from the more volatile parts. So let's see why this happens. Why do code grow stable? And why does that relate to correctness? Well, first of all, code can grow stable because it's dead code. It's simply not even used. And I have to admit that that's my favorite code because we can simply delete it. We can get rid of it, and less code is always better. But code can also grow stable because even if it has a bunch of quality issues, maybe it has been debugged into functionality. It works wonderfully in production, it just does its job. It's a stable and well understood feature area. So it might not be optimal, but code that works is also quite nice to have. When I talk about technical debt, I frequently touch upon legacy code, because the two are related, but they are not the same thing. So let's start by definition of legacy code. The definition of legacy code that I use is this. It's code that somehow lacks in quality and, more importantly, code that we didn't write ourselves. So I want to share a story with you on something that happened to me a couple of years ago. What happened at that time was that I visited a large organization and we did a workshop, right? Basically means I ran a number of behavior code analysis on the code base. We discussed the hotspots, we investigated the findings, and made some priorities on what to fix. And they had two code bases, and both of them looked pretty good. They were pretty solid code bases, right? There were some minor issues, but nothing that big. However, then towards the end of the day, one of the team members suddenly said that, yeah, we have been discussing these two code bases a lot, but we actually have a third code base as well that we are responsible for. So I thought, all right, cool, let's look into that one. And everyone kind of just looked at each other and said, oh, yeah, we don't have to do that. We know it's a mess. So I said, all right, this is really interesting. Now we have to look at it, right? So we picked it up. We did a hotspot analysis on it. And guess what? It turned out that the hotspots in the third product, they were just of the same quality as the product 1 and product 2 hotspots. There was virtually no difference. It wasn't worse in any objective sense of the word. So where was this perception there? Why did everyone think that Codebase 3 would be much worse? Well, it turned out that what actually happened was that the third codebase was developed by a different team in a different part of the organization. And that team was disbanded, and the new team kind of inherited that whole codebase. So the reason the code was hard to understand was due to unfamiliarity. Unfamiliarity with the solution and partly also the problem domain. If it's that quick, all we have to do is disband a team to turn a codebase into legacy code. How quickly can we take your current codebase and turn it into legacy code? What do you have to do? Well, let's see how behavioral code analysis can help you. Again, I'm going to turn to version control data because, like I pointed out earlier, version control data is actually social data. We know who the main developer is behind each module, and this is something we can use to reason about the offboarding risks. And I want to show you how this works on a real-world codebase. So now I'm going to shift to a codebase known as ASP.NET MVC Core from Microsoft. So it's a .NET codebase that's used to build dynamic web applications. And you see a visualization of ASP.NET MVC Core here. It looks very similar to the hotspot analysis that we did on Android. The main difference is the colors, because the colors carry a different meaning. So blue means that this is code developed by the current team. So this is the part where we have active knowledge. We wrote the code ourselves. The different shades of gray, they are like our black holes in system mastery. So these are parts of the code that are written by former team members, right? What we can do now with version control data is that we can simply see what's the impact if we move this code base to a different team, or if we pull the current team into working on something else. By going to version control data, we can simulate an upcoming knowledge loss. And you see it to the right, an example. It's indicated in red because the only thing I did to simulate the knowledge loss here was that I pretended that one of the core maintainers was going to leave. And you see that the impact goes pretty deep. So should I be worried? Yes, I would be worried if this was a real scenario. So how do I act upon it? Well, there are two things I always recommend. The first is simply the reactive approach, right? So let's say that this is a real scenario. It's something that's actually happening right now. What I would do in that case is that I will use this data as input to the planning, because it is an increased risk to modify code that we no longer understand. So I would make sure to schedule some additional time for learning, because that learning will have to happen anyway, and I don't want it to come as a surprise. Another thing that I would do, which is more proactive, is that I will look for an overlap between parts of the code where we lose knowledge due to a potential offboarding and an overlap with hotspots with low code health. Because if I tick all these three boxes, we know that the code is relevant, it's a hotspot, so we're likely to continue to work on it. If it has low code health, we know that this is going to be expensive for a new developer to get into. And third, if we lose knowledge, we know it's an issue. So if I tick all those three boxes, what I would do is most likely before that developer leaves or that team, I would make sure to pair them up with a developer that's staying around so that they can refactor that hotspot together and mitigate an upcoming knowledge risk. So what I wanted to share with you here is that social factors like system mastery influence how we perceive a code base. In particular, we tend to overestimate the complexity of unfamiliar code. So using behavioral code analysis, we can actually get objective data on how the knowledge distribution looks, and we can use that to find an overlap with parts of the code that are highly relevant, like our hotspots.
Building large-scale software systems is never going to be easy. So I'm pretty convinced that we, as developers, we need all the support we can get to make our job a little bit easier. And I hope that this introduction to behavioral code analysis has inspired you to investigate the field in more depth. So I would like to leave you with a number of references where you can read up more on the topic.
And let's start with the tooling. We have to remember that this is a pretty new field. In fact, when I started out working with behavioral code analysis, like maybe 10 years ago, there weren't any tools available at all that could do the kind of analysis I wanted to do. So I had to write my own. And a couple of years ago, I open sourced my first tool suite. It's known as CodeMat. It's available on my GitHub page. I'm still actively maintaining it. And CodeMat is completely free, of course. It's open source, and it's a command line tool that can do all of the basic analysis here, like hotspots and even the knowledge calculations. What I've been working on for the past 5 years is a tool known as CodeScene. So CodeScene automates all this analysis. It automates the visualizations and stuff like the X-ray. And it's also completely free for open source projects. So if you work in that space, it's well worth looking at CodeScene. Finally, I want to point out that I find it truly fascinating how far you can get with the Git client. And I want to show you my favorite example here. Because did you know that if you type git log with the -l flag, then you can specify a function name inside a file and have Git trace the evolution of that function. So that basically gives you the basis of an X-ray analysis right there from the command line. And if you're interested in learning more, I have my new book called Software Design X-rays that covers all these use cases and many, many more. There's also a number of interactive examples on CodeScene.io where I analyze different well-known open source code bases, so feel free to explore the hotspots in your favorite open source package. I blog regularly about behavioral code analysis and technical depth at CodeScene.com, as well as occasionally on my private blog, adamtornhill.com. Now, before I leave time for questions, I really like to take this opportunity and say thanks a lot for listening to me, and may the code be with you. Thank you.